Welcome, everyone. Thanks a lot, Istvan, for accepting our invitation today. It's a great pleasure to have you here. Istvan is a theoretical cosmologist at the Institute for Astronomy at the University of Hawaii, while he completes his PhD at the Johns Hopkins University in Baltimore. Istvan explores the mysteries of the universe using statistics, simulations, and observations. He studies how the patterns of temperature and density fluctuations in the early present universe reveal the nature of dark matter, dark energy, and inflation. He's also interested in the anomalous correlation between the CMB and the distribution of galaxies, which challenges the standard cosmological model. His paper that discovered the largest voids in the universe that likely caused the cold spot in the CMB was featured on the cover of Scientific American in 2015. He has published on various topics, including applied mathematics, computer science, machine learning, general relativity, geoengineering, economics, and epidemiology. And he recently proposed a tether sun shield near the L1 Lagrange point to mitigate the effect of climate change. Today, he will present the ISW puzzle. Istvan, please, you can start when you're ready.
Thank you, Eleonora. It's really a pleasure to talk in this series, which had very, very interesting talks. And today's topic is the ISW puzzle, which actually is the most long-standing puzzle of the concordance model. And it is so, we started, this picture on the right is from 2008, and that's what started this whole ISW puzzle story, and the story is still ongoing today. And obviously, since then, we have other even more significant or more well-known puzzles like the Hubble-constant puzzle and the Lensing law or assay puzzle. But at the time when we did this, everything was so perfect with the concordance model that there was a lot of resistance to this. But this has been confirmed, and even as I will show, it has become even more of a problem than it was before. So before I explain what this picture is, I'd like to acknowledge at least some of my collaborators, and of course, not all of them are here because it would fill this page. I mean, I've been working on this since 2008 with a lot of great people, and but we started this whole project with Ben Granat and Mark Neiring. So they are the only old collaborators I put up. And then on the top line, my Hungarian collaborators have been instrumental in creating models, embody simulations, ray tracings, and predictions for these. And then András Kovács is leading actually a group focused on this effect. And I'd like to acknowledge our students who have been instrumental in on our recent results, Gisela, Christine, and Nestor, who have been working very hard in our group. So on the right-hand side, the original 2008 picture is the stacking of 50 supervoids and 50 superclusters. On the top are the supervoids, the superclusters are in the middle, and then the combined figure with the right sign, obviously, is at the bottom. And you can see that there is a very strong effect. Voids are corresponding to a cold spot. Superclusters corresponds to a hot spot on the sky. And the puzzle part of this, that the effect is, as I will explain, is much bigger than concordance model would predict. But essentially, this picture that you see has been a constant picture since all that time. Unfortunately, or not necessarily unfortunately, but this whole stacking issue has been picked up mainly by the void community. And nowadays, people don't stack the superclusters, and that has mainly practical reasons, software issues. Most of the software to find these superstructures are specialized for voids, and it's very difficult to run them correctly such that you would find the same objects. But at the time in 2008, it was Mark Neiring's Vobos and Zobov software in its original form that was very easy to run in both cases. So just to give you an idea how this looks on the sky. So we use the SDSS, around intermediate low redshift, and found these 50 biggest superstructures. And why did we do that? Because we wanted to check if we can test the integrated Sachs-Wolfe effect. So the integrated Sachs-Wolfe effect is very simple to understand. If you think about a potential well, which would correspond to a supercluster, you can think of your car driving, you take it into empty gear and you're driving down in a valley, then your car will speed up at the bottom. And when you get up to the other side, you get the same speed as you went in, except if the other side is a little bit smaller than you came in, then you gain speed. And exactly that's what happens with the photon. The photon falls into a potential well of a supervoid, but then dark energy, due to dark energy, the potential decays. And on the other side, it doesn't have to come up as high, so it would gain some energy. And the opposite will happen in voids. So void in photon crossing huge voids will lose energy. And this is a linear effect. And because the linear effect is zero in, say, Einstein de Sitter omega = 1 universe, this is also considered to be a smoking gun for dark energy. But there is a nonlinear version of this effect, which is present all the time. That's the Risch-Yama effect. It's essentially the same effect, but you have to do the calculation to higher order. And in practice, from ray tracing, it seems that the nonlinear contribution is at the order of 10%. So most of the effect in a Lambda CDM type universe is the linear effect. And finally, why is this a puzzle? The most important reason is has been since 2008 that the signal at low redshift is too strong for Lambda CDM, but it's not subtly strong. It's like a factor of 4 or 5 more than what you expect, and it's difficult to model. And then the caveat to this is that not all data sets and not all models follow this trend. And obviously, because this has to do with growth of structure, the derivative of the potential, where the simple equation here shows the mathematical form of the ISW prediction. We can learn about the growth of structure, the growth history of the universe, which is related, obviously, to the expansion history. So all this is related to all the other puzzles, which are, related to the same kind of expansion and growth history of the universe. And you can see at low redshift, the state-of-the-art point is the combined DES, BOSS, ISW. You can see that dark energy predicts a certain level, but the actual measurement is much deeper than the CDM prediction. So a quick summary of the measurements in ISW stacking and other results. So the original measurement was using the SDSS, using large voids and superclusters traced by LRGs in 2008. Then later in SDSS, both SPAC-Z, similar results. It was the results, I would say, are inconclusive. I mean, some papers found anomalies, some didn't, but not very high significance. Then the DES was very important because it confirmed the ISW anomalies are also present in an independent patch of the sky. So they not just confirm the original results, which have been confirmed. By the way, the original results were from WMAP, and they have been obviously confirmed by the Planck team from Planck as well. So then I think the biggest thing that we don't fully understand is the DESI legacy survey, which seemed to be more consistent with Lambda CDM than all the other measurements. And finally, our most recent result explored the higher redshift range using the eBOSS VR16 QSO data. And soon we will have Euclid to follow up in the same redshift range. So that was a pictorial picture, but as of 2008, my then postdoc Robert Beck did this figure on the right. And I also show the original Grant et al. 2009 figure, which uses correlations, but it uses ISW correlations, which is rarely done. Basically, we ray trace the data, we predicted the ISW map that corresponds to the data, and then we cross-correlated that ISW map with the data, and not the galaxy distribution as most people do. But on the right-hand side, it's difficult to interpret it so quickly because it has so many different measurements. But basically, the trend is that clustering correlation measurements usually don't show the anomaly. And the anomaly in this redshift range is the difference between the red curve, Lambda CDM, blue curve, AvERA, which is essentially an emerging curvature model that predicts a higher ISW result. And you can, but the trend is basically that the stacking results usually show an anomaly, and most correlation results don't show an anomaly. And some of the stacking results where they stack everything and not just the largest, deeper structures also don't show anomaly. And if you think about correlation is basically an unweighted average, and when you stack everything, it's also an unweighted average. When you only use the deepest linear large voids, then you're essentially weighting the highest signal to noise area. And when you create an ISW map from the data, again, you're giving a different weight. And you can see on the left side, if you do the correlations with the ISW ray tracing, then you actually get typically higher results, but the errors on that figure are so large that it is actually consistent with Lambda CDM as well. It's more like a hint that the ISW is higher than you would expect. So if you're stacking voids and you find that the result is typically 4 or 5 times higher than you expect, it was logical for us to think that maybe the largest anomaly of the CMB Cold Spot, which is shown on this picture, might be also, might be showing individually in the galaxy distribution. In other words, maybe the CMB Cold Spot could be due to a large void. And, essentially since 2008, we have been on the search for such a void, first doing essentially a pencil beam survey with Ben Granat to find if there is but that only constrained the voids at higher redshifts higher than 0.3. And then later we had better and better data. But basically, if the cold spot was due to a large void, we should be able to find it. And to remind you, though, this is like a 3 sigma, depends, if with Bayesian statistic, if you do more and more searches, your significance will go down. So it's 2-3 sigma level anomaly, but it's still the strongest anomaly on the CMB, even compared with, the quadruple, the north-south asymmetry, the axis of evil. People have not been talking a lot about these anomalies. Probably the cold spot is the one that kind of stood the test of time, but maybe, the other ones are also still there, but there's not much work has been done recently on them. And, it took us a long time before we found good enough large and deep data sets to check if there is a void. And here is just a two-dimensional, the cold spot and the corresponding distribution in the Weiss two-mass galaxies. And then we actually created photometric redshift using the Weiss pan-stars survey. And then indeed, we found that, if you, on these slices, you can see that at the very, very low redshift, less than 0.9, right at the cold spot area, you don't see a clear void. But as you go deeper, around, 0.15 or so, a large and deep void appears. And, this is the void that actually got onto Scientific American. Obviously, the artist's impression of the void is very different. It's more menacing than a real void. In reality, this is a fairly mild but very big low density region. So you can see this is like a 250 megaparsec radius void, which is minus, around minus 0.2 in galaxy density. So you shouldn't imagine it like the cover image, that there is nothing in this void. Basically, there is even structure, large-scale structure in this void. There could be even local clusters in this void, but it's a very big initial, it's a very big low-density region in the initial conditions of the universe. So we estimated that maybe, the universe should have only, like a dozen or so of these very, very big regions with such a low density. And of course, really near us, around 0.2, there should be only one. And this is our measurements, counts essentially in different ranges. And you can see the green point is our original pencil beam survey by Grant et al. That was our lowest redshift point because it was too narrow beam to constrain to constrain low redshifts. But if we add that kind of gives us the large, the average, density behavior of the void. Then later, Mackenzie et al. In 2007 did a redshift survey in the same area in 5-degree radius, and they confirmed actually on the left the void. And it's actually, as I said, it's not one big void, but it's a complicated structure that has actually a few voids next to each other, and not many, there are not many very nonlinear clusters. And they also found, that kind of a flying ointment, that they also found kind of control regions, which had maybe the similar maybe similar voids, although a little bit more nonlinear voids if you really compare them, but also some very large clusters, and that region doesn't have a cold spot on the CMB. And I would argue that the left is much more linear than on the right, but this is what has been found. And but then later in the DES, Kovacs et al. 2021 also confirmed with fairly high signal to noise the existence of a large underdensity at very high significance. So I think we can say that the Eridanus Supervoid, as we called it, in fact, Andrej gave it the name Eridanus Supervoid. I think it really exists, and we could argue whether it is causing the cold spot or not. And basically, as Mackenzie et al. Commented correctly, the cold spot, the Eridanus void in and of itself, if you assume Lambda CDM, cannot explain the cold spot because it predicts approximately 4 times lower depression on the CMB. However, if you take into account that four times factor that you find in all supervoid stacking results, it actually will explain the cold spot. And then we also try to do Bayesian evidence, and basically your two hypotheses is, one is that you have two rare events. One is a CMB cold spot, which could be a fluctuation, 2-3 sigma fluctuation. And similarly, you have another, in our volume, you have another very, large 2-3 sigma fluctuation, and then they happen to align. That's one hypothesis. And the other one is that you have one, 2 sigma, 3 sigma fluctuation, which is the supervoid, and it causes the cause. But then we don't have to know how it causes it. We don't have to know any physics, just Bayesian statistics. And then Bayesian evidence favors causality over chance alignment at high significance. And, these figures just show that, that Lambda CDM predictions from simulations cannot really create the cold spot on the CMB. But if you take into account, here are some of the ISW measurements fit on one curve, and I will talk more about this curve, but basically if you extrapolate this to very low redshift and then you put it into your theory, then on the left-hand side, you can see that the cold spot indeed can be explained by the Eridanus void, but you have to have this factor of 4. So why would we have this factor of 4 compared to Lambda CDM? And, one of my favorite solution to this would be an emerging curvature model. And we have our own simple implementation of kind of a zeros order approximation for an emerging curvature model, and we call it AvERA. It's basically a simulation where we change the order of averaging and calculating the Friedman equation. So in the normal simulation, at each time step, you calculate the Friedman equation and you expand the volume. Of course, the calculation is in co-moving space, but the expansion creates Hubble drag and so forth. So you have to take the Friedman equation into account. And of course, if you average the full simulation, the average density always stays average. So nothing really happens. You don't actually have to average, but if you did average, you always would get the same average density. Essentially, it's the same omega. And what we did, we used the separate universe hypothesis, and which posits that if you have a small underdensity or small overdensity in the universe, it will itself behave as if it was a universe with a slightly perturbed cosmological parameter corresponding to the over or under density. So basically, it's omega 1 plus delta that you have to use. And we calculate these Friedman equations in many points in the simulation. Basically, it's a coarse graining procedure. And that's where the zeroth order approximation comes from the fact that we average these Friedman equations, and then we do the time step. So actually, algorithmically, we just exchange the order of averaging, and we got actually, originally, we just thought this is a toy model, but it gives extremely accurate results, which is still, it's a huge surprise to us. And this is my other, it's a little bit of a side track. My other favorite model is the timescape model, which is for emerging curvature. And David Wiltshire gave a talk about this. And yesterday night, I had an exhibition of my painting. So I gave it timescapes. I gave it the title Timescape. So I stole the name for this exhibition. If any of you are coming to Budapest in the next, maybe 2 months and you want to look at it, let me know and I tell you where you can find it. So this is the end of the advertising section. I'm back to emerging curvature models. So emerging curvature models basically can be understood in a very simple way theoretically. So first of all, it is a simulation algorithm. So we calculate something, and on the right-hand side, you can see that amazingly what comes out from these models, even though we start them out with omega equals 1, so there is no dark energy in these models, it will create an expansion history that's very, very similar, although not identical, to Lambda CDM. And you can understand essentially physically what's happening is that if you were to replace the average density with the median density and you solve the Friedman equation, actually you would get something very similar to Lambda CDM. And the reason is that you have a log normal distribution. And on the left-hand side, you can see kind of measured distributions in embodied simulations. And these log normal distributions develop a long tail because of clusters, but the volume is taken over by underdensities. And these underdensities, basically cause you the median or the mode of the distribution is going from zero delta to the left. And that's what essentially this void effect the same thing comes out from the timescape models, that the void effect is dominating this essentially because there are lots of voids in the universe. And of course, if we have this model, we can compare it very in detail with Lambda CDM, and you can see that it gives you something very similar to Lambda CDM, but not exactly the same. So, but that's not a problem. That's actually, that's not a bug. That's a feature because, if you have slight difference with Lambda CDM, perhaps it can solve some of the puzzles with Lambda CDM, like the Hubble-constant puzzle. And indeed, we tried that, and we found that our model can create actually a different Hubble constant. So we start essentially at high redshift with initial conditions that are consistent with Planck, and then we run the simulation forward, and then locally we get a Hubble constant that is slightly different from the 68, say, that is put in originally. And then and there is actually even a free parameter, which is the coarse-graining parameter. And you can imagine that, what I just said, separate universe hypothesis, what scales do I calculate these Friedman equations? And if you calculate the Friedman equation on the full scale of the simulation, obviously you will have no effect. You're back to a normal simulation, right? So you have to have a scale, you have to calculate Friedman equation on several different regions. And then there's also, at the resolution of the simulation, or, at, say, a galactic scale, where galaxies are already detached from the expansion, clearly you cannot use those for your coarse-graining scale. So somewhere in between, there's a scale which might work, and we found that the simulation is extremely insensitive to this scale. So we can change the scale by an order of magnitude, by factor of 10, and then the Hubble constant in the end, or the expansion history, will only change by a few percent. But nevertheless, you can actually fine-tune. That you can find a coarse-graining scale that is consistent both with Planck and with the local Hubble constant measurement. So emerging curvature, as realized by AvERA, can solve the Hubble constant puzzle. However, when we did this, we found one problem, which is that we found that there has to be an opposite sign ISW, even though we found, first of all, we tried to see in Beck et al. What does AvERA do with the ISW? And we found that it predicts, a much bigger ISW effect than Lambda CDM at low redshift, which is great. But we also found that there's a sign change around 1.5, and it will produce a negative ISW effect at higher redshift. And that was very, very puzzling. Physically, we can understand it that, at very high redshift, AvERA behaves exactly like Lambda CDM or EDS. Everything just happens in a linear trajectory. And when clusters start to collapse, actually, clusters and voids originally kind of occupy, I mean, I'm talking about superclusters, the same region, but there's a little bit more nonlinearity because they higher density regions. So initially, actually, there's a little bit more growth than in Lambda CDM. And then once voids start to dominate, there's a transition around, below 1.5, and then you get the voids, a void effect dominating, and then creating a bigger ISW effect. So the prediction is big ISW at low redshift and opposite sign ISW at high redshift. And there is a very, I thought, okay, we will kill our model if we manage to look at this opposite sign ISW effect, because it's probably not there. So once the eBOSS DR16 QSO sample was available, that gave us the first chance to actually cover this interesting redshift range 0.8 to 2.2. And I know that the lower redshift, the state of the art is the DES plus BOSS data does show something very close to what AvERA is predicting. So now we set out to do this QSO sample in this 0.8 to 2.2 redshift range. It's about 5,000 square degree area. It's very sparse, but we only want to look at the superstructure. So we hope it's okay. And it's our best. It's low signal to noise, but it's our best chance before DESI and Euclid. So we are a small team. Essentially this team is led by András actually, and so we cannot do, for instance, blinding, but we try to go ahead as carefully as possible. So our philosophy in our group is that we always start with simulations. So the first thing is that we try to, if we define the data set, we look at simulations, and then we try to get the simulations as close as possible to the data, basically counts, voids, whatever we want to measure. We want to make sure that the simulation is very similar to our data set. Then we do all the work on the simulation. So we do a lot of work on the simulation. We figure out exactly what we're going to do, but we don't touch the data in terms of ISW ever. And then finally, once we measure ISW. So there is no blinding because we are not big enough to have a team that blinds and another independent team that does the analysis. But we try to be extremely careful to avoid the pitfalls, of confirmation bias. So this is how we did it. So we have this MXXL halo light cone, and we used the ray tracing simulation used by our earlier paper with Robert back at 2008. We used on this simulation the 2D void finder method. So we decided exactly what we are going to do, and then we stack this ray traced CMB temperature map because we have both the simulation of our data and the simulated ISW map. So we can do this many times in the simulation, decide what to do. And we decided that we would do, with this, the free parameter, which is 2D void finding, is the slice of the redshift slice. And we found, and also in Beccaro 2008, we proposed this kind of tomographic ISW measurement. If you have photo-Z's, it gives you much better signal to noise. And we had 100 megaparsec slices for the void finding algorithm and 4 redshift bins. So we did that on our simulation, and we calculated the expected ISW signals in this mock survey. And then here on the figure you only see the existing data set, and then the prediction, and then the 4 redshift bins. So finally we simulated the signals and compared. And as I said, my idea was this is the end of AvERA, and we can go on to something more interesting. And we can clearly, you can clearly see that even there's a redshift dependence of the ISW imprint even in the 2D supervoids, even in our mock catalog. But it's always staying obviously negative. And this is what we found. And this was this is one of the goosebump moments in science, when you see something and you say, wow, this is, unbelievable. At low redshift, we indeed, and you see the simulation doesn't have noise because, Lambda CDM predicts a very low, you can see the scales on the bottom. Lambda CDM predicts a very low ISW signal. So we just wanted to see what the signal is. And you can see that the low redshift indeed reproduces the previous results, that at low redshift, you have an ISW signal. It's negative from voids, as you expect. Voids are cold spots, but it's much bigger. There's no surprise there. That's essentially confirming the previous results. But wow, the right-hand side figure, that's amazing. The simulation gives you a cold spot, and then the measurement is giving you a hot spot, as AvERA predicted, which is amazing. And we can talk about significances, but when you look at this figure, and if you have been staring like I have been at the stacking results many times, I just feel that I'm pretty confident. Bayesian statistics actually tells you nothing about the universe. It tells you about your state of mind. It tries to establish the state of your mind in a rigorous way, but in an unrigorous way. When I look at this right-hand figure, I just think that it's very likely that the ISW effect actually changed sign. And of course, we just did, the simple Bayesian statistics of detecting this sign change. And this is only a 2.4 sigma detection. So in terms of Bayesian, my Bayesian state of mind is, this is interesting, but not yet confirmed. And also, it's about 2.7 sigma away from Lambda CDM. And you can see, on the right-hand side, the different measurements, and you can see how it really changes sign as we expected. And also you can see that, if you combine all these different redshifts together, it's likely that you will actually measure something much lower, because the negative part will actually, if you average these out in this redshift range, you will be actually very consistent with Lambda CDM. The only way you can measure this if you really use these different redshift beams. And interestingly, this is also consistent with the famous model plot that maybe there is a stronger growth around what's called the cosmic noon. So that's interesting that there are different, maybe there are hints now of a different kind of growth history, and this sign change actually appears to be consistent with a lot of other things. And one way to look at it is to say that ISW actually constrains the linear growth rate f, and actually there's a first of all, mathematically you can write the ISW delta t ISW in terms of this growth function. So then the A ISW, which is the ISW amplitude, is actually is telling you something about the difference between 1 minus f in Lambda CDM and the measurement. And the lower equation tells you that really, if you have something different from Lambda CDM or any alternative model, if it has a growth function, then you can predict from the growth function the ISW. And of course, you can turn around this equation, and then you can plot growth function measurements from ISW, and then you can compare it with other growth function measurement. And this is a compilation of many measurements made by András. And you can see that Lambda CDM is the solid line, and AvERA is the, dashed dot line. But honestly, maybe AvERA should be the solid line and Lambda CDM should be the dashed dot line, because if you look at the point, there's a very strong hint, and that includes actually the cold spot would be also on this line if you assume that the Eridanus void is actually the, if you believe Bayesian statistics, my state of mind is that the Eridanus void is causing the cold spot. So if you look at these points, maybe individually, not necessarily, they don't reject Lambda CDM because there are error bars, some of them are maybe 2 sigma off from the line. But if you look at all the points and the trends, it's actually amazing how AvERA or emerging curvature, and I think all emerging curvature models, more rooted in GR, would be very similar. So all these models would probably give you qualitatively similar picture, but we have an n-body simulation that we can easily measure this growth function in. So if you look at the kind of the collection of these points, they definitely give you a hint that the dot dash line is probably closer to the truth than the Lambda CDM. And taken together, the fact that we have, the more established, statistically more established Hubble-constant puzzle, and then the lensing is low puzzle, that definitely tells you that something we don't understand yet completely about the growth history, and maybe this figure is a step towards the solution. So to do more steps, I think obviously we will need Euclid and DESI and all the big data sets, but we also have the PanSTARRS-1 photometric redshift survey where Robert Beck actually created PhotoZs. We created PhotoZs with machine learning, so it's very good PhotoZs, and you can see that structure is it's pretty homogeneous. Structure is showing, and it does what you expect. The structure will become essentially smaller as you go in redshift, and you can do more stuff on this data set before this new space-based large area data sets will come online. And basically the first thing that we did, which is because we want to proceed very carefully with the ISW effect, because we cannot do blinding and so forth. The first thing was to check our voids in terms of lensing, and basically Gisela and Christine led this project. Gisela did the 2D and Christine did the 3D void finding, and basically we did the same kind of procedure. We had the data set, the Vice PS1 with very good photometric redshifts. It used the PS1 optical colors and the Vice infrared colors. And then we created simulations from the web sky simulations that describe this data set very well. And then they found voids in these, both with the 2 and 3D methods. And the 2D method, I would say, is very close to essentially Lambda CDM expectations. But you see a hint that the north and south patch is a little bit different. And also there's a hint that at low redshift, maybe there is something different. And it's interesting that the DESI results are actually, the recent DESI results on dynamical dark energy hinge on those kind of low redshift data. And then in 3D, you have a little bit more resolution in redshift. It's a little bit more over the place, but you can again very clearly see that something is happening at low redshift, even though by and large it's consistent with Lambda CDM, but there is a more pronounced north and south difference. So we want to understand better this north-south difference in the data set. And obviously it could be somehow we are not measuring the same depth or the same average density or something like that. We have to fully understand that before we would move on stacking ISW results. So this is an ongoing project, and the next thing would be to find superstructures. I'm insisting that we find both voids and superclusters to have a better signal to noise, and then we will see how well this large data set gives, how consistent it is with our previous measurements. And also there's a preliminary result, not stacking, but actual Weiss PS1 Planck temperature cross correlation done by Connor McPartland. It's in preparation, it's still in very preliminary stage, but it appears that there could be like a 4 sigma measurement, and when we average everything, it's a little bit higher. It's kind of a worst thing that can happen, but this is what the data tells you. It's kind of in between Lambda CDM and AvERA predictions in this range. So it's kind of 2 sigma consistent with both. So we cannot tell, at least right now, from these measurements, but we still have to work on systematics again on this data set. So this is just a preliminary plot. But so these are the preliminary measurements. To finish, this is my summary. So the ISW puzzle has been actually a challenge to Lambda CDM model since 2008. So this is actually the longest standing puzzle, even though maybe it's not the most significant puzzle, although now it's approaching, its significance is approaching, I think, the Lansing is low puzzle, but it's not as significant as at least statistically, as the Hubble puzzle. But it has been confirmed since 2008, and most measurements, most stacking measurements have this behavior. And the majority of the stacking results are a factor of 4 or 5 high compared to Lambda CDM. And the kind of model, the emerging curvature model, AvERA, that we used, you can see that in terms of the expansion history, we are very close to Lambda CDM with slight variations, but these slight variations cause the derivative to be much bigger, and it's the derivative, it's the growth function that is much bigger, and that causes in the end a factor of 4 bigger signal. However, there's a caveat, and that's that's maybe, I think that's actually similar to the Lansing is low anomaly, that some measurements, especially correlation measurements, and some stacking results where they stack everything. In other words, those measurements where they use a uniform weighting, they often consistent with Lambda CDM. However, I would say that using the largest, deepest voids correspond to like signal to noise weighting. So we are so maybe that can be understood. Specifically, the Eridanus void will explain the cold spot, but only if this factor of 4 that found in other stacking result is taken into account. And Bayesian evidence strongly prefers causality over chance alignment. Okay, so the AvERA model, which is a simple approximation to emerging curvature, explains the Hubble-constant and the ISW puzzle, and it predicted a sign reversal at the ISW effect at around redshift 1.5. And I would also note that just now there are now true GR simulations, and those GR simulations will probably give the final word about these, the void effect and everything that we find in these emerging curvature, whether this is consistent with GR or not consistent with GR. It's hard to tell without comparing with those simulations, because obviously our idea is very simple, very physical, but in GR there is no clear way of averaging over volumes what we do. So it's basically driven by intuition, and it has to be checked by rigorous simulations. And I think now, like Haley, McPherson, and others are doing these simulations. So I hope that in a short time span we will find, and I think David Wiltshire talk in the same series were pointing to the same kind of effects. So in any way, AvERA did predict a sign reversal, which is a very weird and very drastic prediction. And then we found this sign reversal in the eBOSS QSO data at the 2.7 sigma level. And that's a 2.7, it's a 2. Sigma tangent actually with Lambda CDM, because Lambda CDM predicts the opposite. So it's a little bit higher significance than the actual sign reversal that measures from 0. So these are hints that the growth function results, from the growth function results that I was showing in the previous plot are very much consistent with these measurements. So the convergence maps of voids appear to be consistent roughly with concordance expectations, with slight variations around low redshift, where the DESI data are hinging. So that's also very interesting. So all this kind of points, we need more data. Every talk in cosmology has to finish saying we need more data. And obviously with Euclid, Rubin, Roman, we will be able to reject or confirm the sign reversal, hopefully at a good statistical significance. And the stacking of the Weiss ISW, Weiss PS1 superstructures is forthcoming. But the right-hand side shows our summary plot. This is our best knowledge of the ISW as of today. And you can see that qualitatively, even quantitatively, it's very similar to the AvERA model. It's not similar to what Lambda CDM predicts. And the significance, is varying all over the place. But, at the very low redshift, the large amplitude is established, at close to 4 sigma level. And so inspired by the recent DESI results and these ISW measurements, and together with all the other results, at more growth at cosmic noon, all the growth function measurements by others, and all the ISW measurements actually suggest a kind of late solution for these tangents. And basically, I would call that a late complexity, something similar to AvERA, even if AvERA in detail might not be the right model, but something akin to AvERA must happen where we are not just simply shifting, dark energy in a very continuous fashion, but there is a curve around it. And I explained why this curve happens in AvERA, like at early high redshift, the slightly mildly nonlinear growth of structure actually increases growth, and at lower redshift, when void starts to dominate, this void effect actually stunts growth, the expansion of void. So that extra kind of complexity compared to many models, like the VOVA model, W0 WA model, you can, that's still a very continuously changing variation of Lambda CDM, and it could not explain these models, unfortunately. So I think this is the end of my talk. So I open up for any questions.
Thank you so much. Thank you so much for the very nice talk. David?
Hi, Istvan. So thank you for a really fantastic talk.
Sorry about stealing your name for my...
That's fine. That's fine. So a number of things. First of all, I was very embarrassed that we had a paragraph about your model in Williams et al. And somehow it got commented out. We're going to restore it in the final version of the paper, which is going to be out very soon. And furthermore, Michael Williams is finishing his PhD this year, and he's doing exactly so. The ISW effect is similar to the AvERA model, is exactly what he's working on. So we hope to deliver the results you're after from Haley McPherson's simulations in the coming months. And in fact, there are other. So I've got another student working on percolation theory and in relation to looking at the same things in another way. So it's the same void statistics, and there's obviously a lot of things that we should be discussing, and we're not very far from Hawaii. So I might send one of the students or myself, one of us should come and visit sometime and discuss some of these issues further, because I can see that there is a lot of there's a lot of things that we should look at together. The timescape model, which appears to be consistent with what we're finding in the void statistics, it lies between Lambda CDM and AvERA, and so what you've done is really fascinating, and we want to talk further.
Okay. Yeah, thank you. It would be awesome to go further, and obviously AvERA is a kind of a very simple embodied model, so I'm excited to see the results what you guys get.
We're also with so deep in voids where you just have where the matter is so not if you're not in a void galaxy, but actually out in the depths where there's just protons and electrons and helium nuclei, then in those regions we need to do the particle stuff. And in fact, so Spencer Magnell, who's a student of Daniel Price at Monash, is looking at that. And so we're looking at blending that, blending in-body, putting in-body things into, adding that to Haley's simulations, because so she's got a resolution scale of 4 megaparsecs at the moment, which is fine for us, because we have to be in
4 megaparsec is plenty for ISW effect. If you that's cool.
So there's lots of interesting things to discuss.
So I mean, I think a visit would be also it's a good idea. So let's keep that in mind. Absolutely. And keep in touch, really.
Yes, indeed.
Yeah, thank you. Pieros?
Thank you very much for the nice summary and talk. I have some naive questions. The first one, I couldn't locate where is the cold spot. Is it on the North Galactic Cap or the South Galactic Cap? And the second,
the cold spot is kind of it's more down, so on the bottom right on the CMB when you have these standard plots. I can tell you.
So that's the south.
I can tell you the exact location if you want to know it. So
it's in the middle of the DS footprint, so it must be south.
So it's LB.
South, okay.
200 LB is 209 and minus 57. So I don't want to, like 200 and minus 57. So B is minus 57. So, but it's galactic coordinates. So the galactic, you like.
Okay, because I remember when I was working for eBOSS and eBOSS, there were a lot of issues with southern catalogs, and apparently there are huge systematics there that are not well known, and possibly there's a lot of theoretical understanding that is missing there. So
even the DES. I mean, if you go back to the plot. You see the DES is like our catalog was kind of like we didn't have the full cold spot in pen stars. It was cutting it up, and even for the DS you can see that it's not the whole, like it is close to the edge. So that's always a problem, because like the middle of a catalog is always better than the edge. So notwithstanding, different, independent surveys have confirmed this. So the WISE PS1 survey, for instance, that we used, it's based on WISE. So WISE shouldn't have this kind of boundary issues, and every object has been selected on WISE, in this catalog. But the photometric redshift, you can again see that it's cut off right at this edge. The photometric redshift, towards the edge could be, not as good as in the middle, but, we tried, to do the best to whatever, the best to do the best, meeting any systematic effects, and we examined the systematic effects. So we did a careful job, but having said that, there is always, I think that's a very fair comment that the cold spot is usually at the edge of these surveys. So it would be good to have but that's kind of, unfortunately, that's geometry, like where the telescope is and so forth. It just so happens to be at this spot. So maybe, I don't know how, I think Euclid will observe this, I'm pretty sure. So we can, I think that will be the ultimate answer, I think.
Thank you. And the other question that I had is about the theoretical estimate. So the integrated Sachs-Wolfe effect is done in one of the gauges. Is there any work that you can have a predicted signal in another gauge and see somehow the theoretical uncertainty that there is there? I expect to be small, but I'm wondering if there is one, and if you have used it in your analysis.
What do you mean by gates? Like other gates?
The gauges of the field in the metric.
Usually, gauges. Yeah. Okay, yeah. Gauge. You mean gauges? I don't think that the gauge should matter so much, but honestly, I don't know the answer. But basically, this has been looked at with GR experts many times. So I'm assuming that the measure, any measurement should be independent of gauge. So when you calculate something, when you measure a temperature on the sky, for instance, that's independent of gauge. So whatever gauge they did the calculation, and I'm assuming maybe they use Newtonian gauges, because the results make sense also classically, then there shouldn't be a problem. I don't expect any gauge issues here, because we are comparing observation, So the theory is trying to present observation. So that would be my answer, but it is not based on me having calculated in different gauges and testing it, that it gives you a different result. So that's my answer.
Okay, thanks, Helen.
Thank you. Marit?
Yeah, Istvan, thank you for the really great talk. But I have one comment and related question. There is even longer, older puzzle in cosmology, and this is why superclusters and voids in the local universe have this regular placement, which we described first in 1994. And my comment is that this regularity may enhance voids, because superclusters are not randomly projected on each other. And this is related to that process that we can have those huge voids like Eridanus voids. And also another comment, in our quasar system paper from 2014, we found that when we plot quasar systems, we can see regularly huge voids between them, 4,400 megaparsec voids, but it's not really highlighted in the paper, because we thought that we have maybe 8 voids and it is statistically not very significant, but it might be related to what you were talking today.
Okay, thank you. That's very interesting. I have to check that. So
well, we are writing about this in this white paper.
Yeah, you can still add the sentence.
Yes,
about
yes.
this in the white paper. So that's a good idea, I think.
Yes, thank you.
Thank you.
Juan?
Well, thank you, Istvan. That was a beautiful talk. Actually, I learned quite a bit. So I'm puzzled still about this redshift 1.5. Okay, so where you change your growth function from below 1 to bigger than 1, and therefore you change the sign of the ISW. Didn't quite get your connection with the stellar formation rate, the Maddow-Dickinson curve. Why did you make such a connection between the star formation rate and the time in which you would expect this ISW?
I mean, this is more
just
like
a coincidence, or is there a reason behind?
No, I mean, it's just a qualitative, it's like some people suggested that maybe growth is stronger and that stronger growth creates more stars. I mean, it's a very, it's not a, obviously you would have to run basically emerging curvature simulations with hydro and star forming, and I think we are very far from that. So we cannot, draw a line, like a clear line, but it's more like I wanted to add like another completely, it's a hint basically that maybe we are on the right track. So it's nothing to be taken too seriously, but maybe, growth is definitely influencing star formation, and this model plot might be showing signs of that. That's all I'm saying. But of course, there are other reasons. Yeah,
that's another connection which caught my eye, which is this what you mentioned about complexity, right? Latent complexity. Yeah. Now, do you have in mind that somehow the cosmic web arises through gravitational collapse of objects that become the superclusters that leave behind the big voids, and somehow you're ordering matter? So you start with a very homogeneous fluctuations where just grow up through gravitational collapse. They order themselves. There is a production of entropy, and these voids become deeper and larger because of this growth of entropy inside. Do you think this is what you have in mind in terms of complexity, or what did you have in mind when you?
I think I had in mind actually something much simpler. So if you're in the linear regime and you're considering very large scale fluctuations, like 100 megaparsec scale fluctuations, or at least 50 megaparsec radius fluctuations, then initially at high redshift of 10, redshift of 50, whatever, you will have on average in a Gaussian distribution the same number of high and low density regions, right? And they will also take up the same volume essentially. So initially everything just grows linearly, but then in a gravitational instability, actually slight over densities grow a little bit faster because they are, there's no limit. There's a limit. -1 is a hard limit for low density regions, but you can always pile more material in. So there's a slight advantage in growth compared to.
So you mean you get something like a log normal where you have high tails at the high end and very large suppression at low end.
Exactly. So this log normal starts to be created by first just you have a Gaussian and this tail is growing slightly, and this tail first is influencing growth because the volume of low and high density regions is still comparable, but the high density regions have higher density, so they grow faster.
Right.
And that's what's happening at high redshift. But eventually the voids just blow up and they take over all the volume. And even though the growth is still, like obviously very big regions are just virializing, so they don't grow anymore, but very large superclusters are still growing a little bit faster, but they don't take up as much volume as the voids, and therefore the void effect is dominating. And then the void effect is actually stunting growth, and is stunting growth according to this curve faster or more effectively than Lambda CDM. And this is why you get this complexity, this late complexity, that first you have this extra growth and then you're stunting growth more. So
so just like you described it, if you would have started with a primordial non-causality with a significantly large tail, this is something that we envision due to quantum diffusion during inflation. So the fluctuations are no longer Gaussian; they're actually are more like a log normal. They're elliptic functions, but they're much higher tails and high density. Then you would quick start structure formation by having this bias with respect to, they're not symmetric now any longer, and therefore you have a much larger bias towards larger densities. So you would start much earlier. So perhaps this whole process that you were describing is a consequence of a non-Gaussian initial condition on scales which are smaller than those of the CMB. It
could very well be. I mean, basically, in terms of measurement, so obviously AvERA is a very simplified model. It's not completely.
But you could reproduce it perhaps with a very large non-Gaussian.
But non-Gaussianity is produced even without primordial non-Gaussianity. But you're right that on very large scales you would produce more non-Gaussianity. Clearly,
you could explain perhaps why you see objects as far as redshift 14 fully formed, like James Webb Space Telescope is finding. If you have this non-Gaussian.
Yeah, and it would be actually what Maret was saying would be also consistent with that, because you would have bigger fluctuations on very high redshift than you would expect from on the. So I think right now what I'm really advocating is this late complexity, and I think very few models actually have this late complexity. So it down selects to a lot. If you think that this is something serious observationally, then you want to think about all the different kinds of models, including primordial non-Gaussian, that causes such late complexity. So I think that's a very interesting comment.
So I'd like to comment further that this idea of mine of generativistic entropic acceleration goes exactly in the same direction by producing entropy, which acts as like a force, like a negative pressure, like a viscosity, essentially, on the fluid. And this makes voids deeper, and at the cost of superstructures, of course, as well as giving rise to the acceleration without the need to introduce any cosmological constant. But of course, we can discuss later.
Yeah, okay, that's cool.
Thank
you.
Thank you.
Thank you. Another question, Umut?
So thank you for the very nice talk. Yeah. Okay. So I was referring to the past studies with imaging legacy surveys and the eBOSS survey where they couldn't detect ISW, or they detect in agreement with Lambda CDM by using different filtering technique. And do you think the filtering or what may be happening of this?
I didn't hear the most important part of your question, sorry. I mean, I understand the question is about why, maybe the question is about why a few, especially DESI legacy survey, Hangelaw is not finding the similar results as we find. And actually that's something of a puzzle. And I think what I would like to do is some kind of a sprint with them, like with Cy and John Peacock and our team, to figure out what exactly is the difference, because we, I briefly talked to John in London, and he said that they really tried to follow our recipe. So that's all the more puzzling, but I don't know the answer. I think we would have to go through it in detail. So I think that's the most, but I would say that the DESI legacy survey is the most important kind of question mark in this. It's a puzzle within the puzzle, because most other things are very well described by what I said, that when you're stacking results in basically high, deep and large voids, you always find this excess. I don't know if this, I don't know. Yeah, is that roughly the right question? Because I couldn't see the chat.
Yes, that was the right question. Yeah, I think this is happening for most large voids, because previous BOSS study in 2016, they didn't do radius analysis, and they find a very good agreement with Lambda CDM there. Okay. But yeah, it's a very interesting avenue.
Yeah, so I think that has to be taken very carefully, but basically I would say the majority of the stacking results, with maybe with this one exception, where they used criteria to characterize the depth and size of the voice. Usually we have this lambda parameter, but anyway, that's too technical. you know, if you use this lambda parameter that you can basically calibrate in your simulations, and then you find, you know, the structures that you expect to be linear, then you find this excess.
Thank you.
Thank you so much. Okay, if there are no other questions, I think we can thank Istvan again for the very nice talk.
Thank you. Thank you for having me. This was really fun and very good questions and
Thank you.
reactions. And thanks a lot.